everyone, welcome to the shop and welcome back to the Trent Pinion Mill build. Get ready for lots of fly cutting this episode. Most of the work here has been on the column casting, including machining the dovetails. I'm starting with the front surface that will become the male dovetails for the knee. The bulk of the machining on this casting is just to remove the rough cast surface and square things up and get them roughly to dimension. None of the dimensions here are really critical, so you might notice in this footage that for the most part I'm just using a steel rule to measure. I'm using a really long end mill here so that in the same setup I can make successive passes down what will be the bottom of the casting to get a surface that's good and square to the front that will become the dovetails. This is a good time to mention that the quality of these castings is just excellent. All of the voids are absolutely minuscule and very close to the surface. The machinability is very consistent. I didn't encounter any chill spots or anything like that. I'm really happy with this kit. As you can see here, I did eventually decide to start covering up the exposed areas of the mill table and the dovetails on the vertical column just to keep the cast iron dust off of them. I'm sure most of you know this already, but for anybody who doesn't, cast iron swarf is real bad for machine tools. It's quite abrasive. So you always want to take steps to thoroughly clean your machines afterward. And like you see here, do what you can to keep it off the machine in the first place. The further along we go here, the more likely you might be to ask yourself why I'm not doing certain operations in the same setup, why I'm going back to revisit earlier setups to make finishing passes, why not machine the dovetails at the same time I was doing the initial setup, milling the front surface of the portion that will become the dovetails. And the answer to that is warpage. This is cast iron, but the same would apply to most metals. When you start to machine them, it releases internal stresses that start to act on each other differently. and you get warping of the material. It's not typically noticeable by eye, although in some cases it can be. For this application, there are certain surfaces that we want to treat as reference surfaces that should be square and or parallel with other surfaces. And of course we want the dovetails themselves to be nice and true and straight. So in general, what I'm doing here is roughing everything out. You'll see me go back and make a couple of finishing passes on the rear of the column as well as that front face again, and then mill the dovetails. You might also be asking yourself what happened to the shop audio that you've been hearing up until now. Let's just say that if you're planning on using video and audio footage in your shop that's sped up 3,000 to 4,000 times, don't listen to electropop, because it'll sound an awful lot like either a phone ringing or a 9600 baud modem. Unfortunately, the budget didn't allow for one of Randy Richards' dovetail cutters to be ordered for this project. That certainly would have been my preference. What I'm using here is an HHIP brand dovetail cutter, 3/4 inch diameter. Of all the inexpensive dovetail cutters, it looked to be the most promising, and the jury's still out as to whether it will hold up for the duration of this project, but so far so good, and on visual inspection, it seemed to be fairly well made. It cost about $22 from Amazon. Let me know in the comments whether you think this thing will last the entirety of the project. After starting on the second half of the dovetail, I noticed that the milling forces were starting to lift the part up a little bit in the vise. So I stopped everything and went back and clamped it down using a set of step clamps to keep it from lifting again. And I finished the operation on the one side, then went back and did another pass down the other side, just to be sure that both of them were parallel with each other. Now it's finally time to make a set of screws to hold the column to the base plate. I'm starting with some W1 drill rod. The drawings call for M5 countersunk screws, but I'm substituting number 1024 Philister or cheesehead style screws. The countersunk screws would be a lot better for self-locating to keep reliable alignment of the column to the base plate upon disassembly and reassembly. I really prefer cheesehead screws just generally for their aesthetic, and I felt up to the machining challenge of turning some shouldered screws that located perfectly within countersunk holes in the base plate. After facing all of the screw heads to the same thickness, I took them over to the Horth milling attachment to slot them. When I drilled the holes through the base plate to mount the column, I was careful to use the hand wheels, the analog readout if you will, to position the spacing between all of the holes. That made drilling the corresponding holes in exactly the right location pretty straightforward on the underside of the column. All I had to do was lay out and line up the first hole to the layout marks, and then position the rest of them, again using the hand wheels to get the correct locations. My backup plan in case something went wrong there, given that I'm not using the countersunk screws, was to drill out the holes in the base plate a little bit oversized to get clearance enough for everything to fit, and then drill through for a couple of dowel pins or steady pins to keep the column located on the base plate. Lastly, we need 3 screws to hold the knee support down to the base plate. These will be number 632. And now finally we can screw the components together. We're going to take a real-time interlude for a moment, because something came up that didn't make a whole lot of sense to me. If you read about fly cutting versus mill tram pretty much anywhere, it will be stated that if your mill is perfectly in tram, you will see a cross-hatching crisscross pattern in your fly cut surface, which makes total sense, as the leading edge of the fly cutter is cutting. When the trailing edge of the cut comes along, it will scrape the surface and leave that crosshatch pattern. It's an indication that the spindle is perfectly perpendicular to the work, so that the distance from the work to the cutter when the cutter is in this orientation is the same as when it's in this orientation. While it might at first seem like more of a cosmetic issue, it really goes a little bit deeper than that. In a case where the mill is out of tram, we'll exaggerate this a little bit here and show the fly cutter tilted this way. So here your mill would be out of tram along this axis. As the cutter sweeps across this way and makes a cut, what you're left with is a concave surface. It'll be dished a little bit. Now, obviously, when the mill is out of tram by just a few thousandths of an inch, that dish surface is, not going to necessarily be noticeable by eye, but it will vary a little bit based on the diameter of the fly cutter. The larger the diameter, the more that effect will be exaggerated. And then, of course, when the cutter rotates around this way, it won't touch the work at all because it's, up off at an angle like this. So you'll see your fly cut surface with no cross-hatching marks at all. And if you measure it, you should measure an at least slightly concave surface. One has to imagine that there's a little bit of a range in the tram before you would start really noticing this effect. For example, if the mill was out of tram by, a couple 10,000ths of an inch over the sweep of the fly cutter, there's a pretty good chance, at least on the small benchtop mill drills like a lot of us use, myself included, that simply the rigidity of the setup versus the cut will cause the fly cutter to deflect enough to still produce this cross-hatching pattern just due to spring in the leading cut. Even though the mill is maybe slightly out of tram, you would still get that cross-hatching pattern. So while I was perfectly happy with the cosmetic finish of the fly cut surfaces on this column casting here, I did start to wonder as I was reading why I was getting this non-crosshatch, although pretty looking, finish when I had gone through great care to tram the mill into place. And having used Stefan's epoxy and copper wire technique, I became, increasingly concerned that maybe I had just epoxied my mill out of tram. Yet repeated checks going back afterwards, it comes in very well trammed over a 9-inch circle along the x-axis. It's well under 0.5 thousandths, and along a 6-inch circle on the y-axis, the same, well under 0.5 thousandths. So could it be that my setup in that little mill was rigid enough and my cutter sharp enough and my depth of cut shallow enough that just that very, very slight out of tram that I knew I had, your tram's never going to be absolutely perfect in the mill. Maybe that was, enough just not to leave this crosshatch pattern. What you see here is the column casting setup on a 1-2-3 block, just to have some clearance for the plate on the bottom here on the surface plate. And I've got my HA low test indicator on here that reads in 10 thousandths on my surface gauge back here. And I started doing some tests, just sweeping this across the surface to see just see what the geometry of this thing looks like at a very, very minute level. It's a little bit tricky because even though the finish feels nice and smooth, it does register on the indicator and cause it to flutter a little bit. If you look, we're reading along the front side here, what is it, about 2.5 10 thousandths, 2.5 tenths. So I don't expect all these surfaces to be absolutely perfectly square within, a few 10 thousandths realistically. This is right off of the mill. So I expect there to be, a gradual deviation across the surface. But what I'm hoping to not see is evidence of a dish in the surface. So this reading should not go up and then back down as we run along the surface here, at least not significantly. So in the middle, we've got now just a bit over 4 10 thousandths. So 1.5 tenths. And then along the other side here, we've got 5 tenths. So we've got a difference of, and depending on where along the surface you check, and depending on how many of the checks you do, I'm getting between 3 and 4 10 thousandths from this side to the rear side, and generally a pretty nice linear taper to that reading. There certainly isn't a scoop in the surface that I'm reading along this at all. You can see, See, now return to the same position we were at. We're at about 1 10 thousandth. So, that's again, that surface variation there is really making this difficult. But we're talking about 10 thousandths here, so this is really difficult stuff to repeatedly measure, without a perfect surface finish. And this obviously is A little bit of a hodgepodge setup here, but for the purposes of checking the surface in regards to a dish caused by out of tram during fly cutting, it's sufficient, and I'm very happy with the results, but I'm still left a little bit perplexed as to why I'm getting these results with this surface finish, without the cross hatching along it. So again, my best guess is that it was a really light depth of cut. I know that it was about 3 to 4 thousandths depth of cut on my finishing fly cut. I know the tool was good and sharp, so I guess between the light depth of cut, the tool being very sharp, and the mill being, just the hair out of tram that, generally any mill is going to be, I guess there wasn't enough of a spring to the leading cut to cause the trailing cut to drag at all, even though we were talking about very, very small amount out of tram. So when we're talking about the tram of the mill being along one axis, for example, it was half a thousandth over 6 inches, let's say. If I'm running a fly cutter that's about 2 inches in diameter, it's actually 2.2 inches in this particular case. This part is 1.5 inches wide. That's roughly a third of the tram circle that I measured on that axis. So about a third of a half a thousandth, this is 1.5 to 2 10,000ths that this fly cutter I was using, the fly cutter itself, would have been out of tram measured at its extremities. So I would have guessed that would be little enough for it to drag and expose a cross-hatching pattern, but apparently not. Very, very interesting though. On that note, I think we'll wrap it up for this episode. Tune in next time when we'll start machining on the knee casting. Thanks for watching.